Today we're going to talk about finesse. This has to do with optical cavities, and really what we're talking about is going back to our etalon conversation. We have transmitted intensity, I sub t, and frequency. Depending on the finesse of the cavity, you could have differences in the transmitted intensity of the light that's propagating through your etalon. Just as a quick reminder, etalon is two parallel surfaces that act as mirrors with reflectivity R and index of refraction N. In a lot of the cases that I work on in the infrared, N would be for germanium or air gap, depending on what you're doing. This length here is L, and depending on the frequency of your laser, broadband light source, there's going to be constructive and deconstructive interference as light propagates through, bounces here and back in this cavity, and that's going to be a function of the wavelength relative to your separation distance L between the two mirrors. And so depending on your reflectivity, as reflectivity increases, your sharpness of your features that you capture on the other end, as you propagate through this cavity, will increase. The sharpness will increase. So just definition of finesse, fancy F, is pi times the square root of R divided by 1 minus R. And now, why is this important? How does R affect the overall sharpness that we're talking about here? One way to conceptually think about it is, let's say you have your parallel mirror surfaces and you have poor reflectivity, so as your light transmits through, maybe you get one bounce, maybe something like this, and out you go. If you were to have really high reflectivity, so let's consider this a whole new set of parallel surfaces. Let's say you have just a ton of reflections here before you come out. So what's happening is, with each reflection, you have an opportunity for constructive and deconstructive interference. And as that increases, you essentially have less light leaking out. At least that's the way I think about it. So every time you have a reflection, the troughs get lower and the peaks. I guess it's just the troughs get lower as more light exits, and you would increase the peaks as well because you have constructive interference. That's the way I try to conceptualize it. As I learn more about these interferometers, I think we'll learn and clarify, at least conceptually and then eventually mathematically, how this works. The overall point of this one is just how to calculate finesse. And just to give a couple examples, if your reflectivity is 0.5, you'll have a resulting finesse of 4.44. If your reflectivity is 0.95, it'll result in something like 61. And a lot of mirrors, for example, if you go to Thor Labs and try to find a mirror to buy, it's pretty common to get something greater than 90. Not so easy to find something at greater than 98 that are very application specific. But just to give you an example, 99% reflectivity gives you a finesse of about a little over 300. Hope that's helpful. We'll keep this series going and see if we can learn about Fabry Perot etalons some more. Thanks.